All right, and we are back again. Uh, Dmitry is going to talk about microservices and single-digit microseconds latency. Dmitry?
Hello guys and welcome to the dark side. In today's talk I wanted to tell you about how we in Chronicle achieve single-digit microsecond latency for our microservices. Before we dive in, I have a little disclaimer. This talk has a lot of disturbing shock content, a lot of controversial points, so it is unsuitable for children, pregnant women and Spring developers. You've been warned. Let's go ahead and get started. First of all, let me introduce myself. My name is Dmitry Pisklov and I'm a developer at Chronicle Software. Chronicle Software is a company specializing in low latency, ultra low latency development. Our founder and our CEO is Peter Lorre. You probably have heard his name. He's Java champion. He's got most answers for Java and JVM on Stack Overflow, and well, generally very famous guy. Now, the brief outline of what we're gonna talk about today. First of all, we'll look at the example of the microservice application that we've developed. Will be slightly stripped down architecture example without too much details. Then we will talk about what is latency and how can we measure it. And finally, the biggest part of the talk would be about reducing this latency. So first of all, let's start with an example so that we know what we're talking about. This is a skipped down architecture of the real world trading system that we developed. This system, well, it might seem scary at first glance, but we'll go into a little bit of details further on. So the input of this system are the fixed messages coming in from some fixed gateway. We transform them somehow and we put them as an inbound messages to the control system. Control system is our main core system which has some state in it. And based on the inbound messages, it makes some decisions and emits the outbound messages. Those outbound messages sometimes transformed and sent as fixed messages to the outside world. So the critical path of this system looks like that. You've got fixed messages in, you've got the transformer, you've got the control systems with the state, you've got another transformer, and you've got messages out. And also you've got a couple of sidekicks, which are called strategies, which basically respond to the outbound message flow from the control system, and if they detect the need to adjust the control system state, they inject some more input messages into it. So all pretty simple really, and for this system we've got a benchmark. So this system with the throughput of over a million of messages per second, we can achieve latencies under 10 microseconds, which I think is pretty impressive. So how we do this, we will talk about it. But before we go ahead and talk about how we do this, we need to talk about what is latency. What did we measure on this previous slide, and how? So what is latency? Latency is usually just described as the time it takes from sending the request to the system and getting the response back. When we talk about latency in microservices, well, we mean exactly that. But in microservices, it consists of two main parts. First part is the actual service response time, basically the time it takes to unmarshal the request, compute the response, and marshal it back. And another big chunk is IPC latency, basically the time it takes to deliver the request from the user to the service and deliver the response back. How do we go about measuring latency? Well, it should be pretty simple, right? We send a message, we wait for a response, we time it. The two tools that we use in Chronicle for measuring latencies and in general for benchmarking are JMH, which is probably everyone knows about. It's for micro benchmarks. And the other tool that we developed in Chronicle, which is inspired by JMH, is a JLBH, which stands for Java Latency Benchmark Harness, which we specifically developed for latency benchmarking, not for micro benchmarking, but for macro benchmarking. Documentation and examples for the JLBH are on GitHub. It is an open source project, so feel free to use it. Feel free to report to us any issues you have, any questions, Stack Overflow. So the main benefit of JLBH over JMH is that you've got your code running in context. You run up the full stack, you put the probes, and you measure the time, measure the latency between those probes. You can do the variable throughput. For each throughput numbers, you can estimate the max tail latency for this particular throughput, so you can provide SLAs to your clients that, depending on the throughput, depending on the load, that is the response time we expect. Then JLBH accounts for coordinated emission. I think everyone knows what it is. If not, please follow the link. JLBH allows you to put various sampling points in the code. So basically, you don't have just two probes end to end. You can insert as many probes in the middle as you want. So if you have system, for example, with 10 microservices, you can put sampling points after each of the microservice so that you know exactly how much it takes for each microservice to respond and what is the end-to-end latency as well. This is an example of running JLBH. Here you can see the output, and well, it contains everything that you would expect from the benchmark. It contains various percentiles, numbers for various percentiles, the microseconds it takes on average, on 90th percentile, and so on and so forth. But the interesting bit, it also shows you the percentage of variation between those results. And in this case, we can see that the 50th percentile is, we can kind of trust it. It is just 5% variation, so that's acceptable. But anything beyond it, 90th percentile, 99th percentile, and so on, are statistically invalid. The reason for this is just some random benchmark I ran on my desktop machine with some other stuff running. So that's not really ideal environment for benchmarking, and that's what this benchmark result shows. So let's go ahead and talk about fighting latencies in our software. Now that we know what is latency and now that we know how to measure it, we can start reducing it. And the first and foremost thing that we as Chronicle advocate is using less code. The less code you have, the more performance you get. And well, ultimately the fastest code is no code. We all know that. And the quote here by Antoine de Saint-Exupéry is the quote that is our company's motto. It is on our website, on the main page. Basically, Antoine de Saint-Exupéry says that perfection is achieved not when there is nothing more to add, but when there is nothing left to take away, which is perfectly applicable to development, to the software development. The more skimmed your code is, the better it performs. And also the easier it is to reason about the correctness of the code, which is also important. Also, JVM itself cares about the size of your code, cares about the method sizes. You will know that there are flags to control the size of the methods that JVM will inline. By default, they're fairly small. And two very large methods are not even JIT compiled, so they will be running in interpreted mode that will be really, really slow. So even JVM suggests that we should be really using smaller methods, we should be using less code. Now, when we talk about less code, we must talk about specialized code. So the more specialized code, the more assumptions you can make about the code, about the environment you're running in, about your users, about how your users are going to use your software, the less code you need, the less checks you need, the less conditions you need, less data you need to write, and obviously more limitations, but the more performance you get out of this code. So there is an example here of two benchmarks, basically the same benchmark with two different products. We have the main product Chronicle has is the Chronicle Q. Pretty much all our products are based on Chronicle Q. What is Chronicle Q? We will talk a little bit about later. Basically, it is messaging system. Let's leave it there for now. But it has the specialized version called Q0, which only supports one reader, one writer. And that allowed us to remove loads and loads of checks, loads and loads of conditions, and speed it up drastically. So bear in mind, this graph is logarithmic. So the difference on 99th percentile, for example, is not twice, is actually 2 orders of magnitude. So that's basically the what you can achieve by specializing the code without changing logic. It's the same logic, it's the same algorithm, just slightly more specialized with slightly less checks, with slightly less conditions. And when we talk about specialized code, we might start talking about primitive specializations. So like we don't want to use a standard collection, for example, for primitives. We want to use some specialized collections and maybe some other specialized type of objects which specifically work with primitives. As you know, in Java you can't really use something that is designed for objects with primitives, because then you will have boxing and boxing cost, and well, that's pretty expensive. But writing these primitive specializations for everything is not very cost efficient. So what we use for this is code generation. So code generation is in general very nice solution to produce optimized code where you need the same type of code, the same kind of code for different tasks. You just use you create the code generator which generates specifically optimized code. Another example is marshalling and unmarshalling code. You create an object and then you want this object to have some marshalling and unmarshalling code. You don't want to write it by hand because usually this code is pretty boilerplate, so you can use code generation for that. Nice example of code generation are Collabor collections by Roman Leventov. It only generates actually used methods. So you define an interface, or abstract class in this case. You tell it what methods you want to use. So in this example, we want map where keys and values are longs, primitive longs, and we're just gonna use these 6 operations. We just want to put, to get, to check if the map contains key, and probably iterate for each, and well, clear and have a look at size. We don't need any extra map operations, so Collabor will only create what we actually asked for, and trust me, it works really, really well, and it is much faster than the standard map you would find in JVM, in JDK. Now, the controversial topic, multi-threading. For microservices, we advocate that threads are bad. Threads are evil. To put it slightly softer, it's not the threads are evil, it's multi-threading that is evil. It's the thread switching that is evil. So what we want is we want microservice running in a single thread, using the event loop for all the input-output operations, and we can pin this thread to the dedicated CPU. We can tune it further, and that's the best way to achieve low latency on this microservice. When we need to share the data, we would be using the shared memory and CAS operations for synchronization. We don't want to block, we don't want to do like full locks and so on and so forth. we only want CAS, we only want shared memory, and only when we really need to share some data. Don't share everything, just share what is really needed to be shared. Now, when you do share, you think about memory barriers. Think about what memory barriers you actually need. Don't just go for CAS for every exchange operation. You don't need it. You might go get away with volatile, or you probably don't even need volatile semantics. You probably just need store barriers. You just need an ordered put. So the difference between volatile put and ordered put is in speed. So what is volatile put? It is a load store barrier, which basically ensures that you flush the data you write right to the memory, and when you do volatile reads, you ensure that you read from the memory, not from the CPU cache. That is expensive. That doesn't come for free. But store barrier just ensures that your stores are in order. That it doesn't care whether your store makes it to the memory right now or not. So what is the difference in terms of speed? There you go. The first is lazy set, which is ordered, which is store barrier, and the second is volatile. And as you see, the numbers are pretty self-explanatory. There is 20% difference in cost between volatile and ordered put. And by the way, on x86 architecture, the ordered put are actually NOP, because x86 guarantees ordered stores anyway. Now, how well do you know how efficient JDK data structures are? In most cases, they're not. And that really applies to most general purpose data structures. So as an example, hashmap. Hashmap put operation creates the new object every time, and every time you remove the entry from hashmap, it deallocates this object. So you basically creating garbage, you need garbage collector to do some work collecting it, and we'll talk about garbage collection slightly later, but for now we don't want garbage. That's the main point. So don't use standard JDK collections. They are not good for low latency. They are general purpose. Same really applies to any third-party library framework. If it is general purpose library, if it is general purpose framework, it's probably not good for low latency, especially for ultra low latency. Spring is probably the best example. If you're using Spring, you're not writing ultra low latency code. Forget about it. Just either use specialized libraries which are just specializing on low latency, or just write code yourself. Don't use some random frameworks, and especially don't use frameworks for the sake of using framework. And don't be afraid, if you know what you're doing, don't be afraid to use unsafe. I have an example of how we used unsafe to speed up our networking by cutting off some safety nets that JDK developers created to prevent us from shooting ourselves in the foot. The details are there in the blog post linked, because it's fairly lengthy and slightly out of scope for this talk. So if you're interested in details, please visit the blog and have a read. But for now, what the important takeaway is the numbers. So by using unsafe and by bypassing some of the internal JVM mechanisms, we achieved consistent 1.1 microsecond improvement on our network I/O, which might not sound a lot, but it's relative. When we talk about total average numbers for I/O, and they are in 5-7 microsecond range, 1 microsecond is actually significant. It's just under 20% difference. So that is pretty a lot. Obviously, your mileage may vary. You are welcome to try it yourself, test it yourself in your own conditions. The code for this is in the Chronicle Network library. It is open source, so have a visit, have a play. There you go. Now, how often in your code do you wait for some conditions? Do you wait for something to happen, for some message to come, for some flag to become true, whatever? Pretty often, usually. And there are different styles of waiting that we can use in Java. The first thing we probably learn as a Java developers when we talk about concurrent programming are the wait notifies. The wait notify involves acquiring the monitor, which is really slow. So the other option is you just do thread slip. That's pretty slow too. Both these options are stalling the CPU, basically slowing the CPU, changing the states of the CPU, and so on. So returning from wait notify, returning from sleep are slow options. The fast option is waiting. While waiting for the condition, you just do thread yield, allowing other threads to do some work while you're waiting. But the fastest option is just busy wait. That is, while we're waiting for condition, do nothing. Just spin, burn the CPU. This will give the lowest latency. This will never allow the CPU to slow down, to decrease the clock speed, and so on and so forth. It will just burn it as much as it can, but you will get your response immediately when the condition is true. But obviously that's not very environmental friendly, so don't show this to Greta Thunberg. Now, we all work with character-based data a lot, so we all know that strings are immutable, which basically means that using strings is expensive. Any operation on string is expensive. Any operation on string involves creating a new string, so we all know that we need to use string builders. Not everyone knows, though, that you can share the string builders and you can pool them. So if you're single-threaded, then you just reuse the same string builder. If you happen to use multiple threads, then you still can reuse string builder, but you can put it in a thread local structure. So I will show the example of this slightly later, but also there is a library called Chronicle Bytes, which implements a string builder semantics, but also it does so much more. Feel free to have a visit. It is open source. It is in our repo. Have a look. It can do a lot. It can work on heap or off heap. Pretty much all of its operations are garbage collection free, so you modify the data in place. There is no garbage collection involved. There is no garbage, and it can do much more than String Builder can, and it's very convenient when you work with string-based, with the character-based data. Garbage collection. In microservices world, in ultra-low latency microservices world, garbage collection issue is pretty simple. We don't want it. Even the minor garbage collections are not acceptable for us. They're too slow. They take milliseconds. If we are talking about SLAs in microseconds, then millisecond delay, 1 millisecond delay even, is way too much. We just can't afford it. So what we want to do is we want to avoid garbage at all costs, avoid any garbage collection. So there is nothing to talk about tuning garbage collection, because we don't want to tune it. We just don't want it to happen, right? To do this, there are multiple techniques. One of the techniques is to reuse objects, especially when you marshal and unmarshal objects from the wire. An example code, pretty simple here, is we create an object which we're gonna reuse, and when we receive the data from on the wire, we just marshal the object, or rather unmarshal the object, into this object that we have there. We process it, and then we reset it again, ready to be reused. Now, another way of reusing, if you can't reuse objects, you can pool them. and then you don't reuse the single object, you reuse multiple objects. But the technique that we use most of all is we use off-heap memory. When you use off-heap memory, you are not bounded by garbage collection. Anything you do off-heap stays off-heap, and garbage collector doesn't know about what you're doing there. So that's a very useful technique, and and we use it all over the place. Now there is this example that I promised a bit earlier of string builder pool. So that's the pool that we use in our code. It basically has a thread local field, final thread local field of string builders. So basically you have a string builder per thread, which whenever you need to use a string builder, you just call acquire string builder, you basically reset it, and it's ready for you to use it. Just don't forget to reuse it. Be green. Now, we talked about writing the code with latency in mind, but that covers one piece of the latency, of the service latency, that is the computation time. Now, let's talk a bit about inter-process communications. As we all know, the fastest writing and fastest reading is to and from main memory. Well, obviously right after the CPU caches, but that's we cannot really control. So always think about mechanical sympathy when talking about keep CPU caches, by the way. So if you don't know what's mechanical sympathy, follow the link, as it is again slightly not in the topic of this talk. Disk I/O is probably the slowest. Disk I/O is usually slower even than DC local networking. And well, we all know that UDP is faster than TCP, but even comparing TCP networking with Disk I/O, TCP networking within the data center is usually faster. Now, in Chronicle, some time ago, well, more than 5 years ago, we thought, what if we can write to main memory and basically use this speed of writing to main memory while letting operating system to flush those changes that we make to memory, flush them to disk. And we thought, well, that's a pretty cool idea. And apparently, there is implementation for this idea already out there in the wild. This implementation is called memory mapped files. What is memory mapped file? Memory mapped file is the chunk of memory that operating system maps onto the some chunk in the file. So basically, you say, you tell operating system, could you please give me the memory mapping for this file for this range? And the operating system says, okay, yes, there you go. And you write to this block. This is just a block of memory, so you just write to this block as you write to the normal memory. And asynchronously, operating system flushes those changes that you make to this block of memory to disk. The important thing here is that this memory mapping is shared between processes, effectively providing us with a shared memory inter-process communication. So basically, when process 1 asks for the chunk of the file, for memory mapping of the chunk of the file, and process 2 asks for the same chunk of the file to be memory mapped, the operating system returns exactly the same block of memory. So when you write to this block of memory from process 1, the process 2 immediately sees what you've done, even though these changes are not flushed to disk yet. So you're effectively using all the benefits of shared memory communication while operating system provides you with persistent messaging. So based on this principle, there is the library called Chronicle Q. It is open source. It is free to use for everyone. It uses off-heap memory and memory mapped files, and it is really fast. How fast? It achieves 4 microseconds inter-process round trip on a desktop box, on my particular desktop box, for a kilobyte long message. That is for the message to go out of process A into process B sending the response back, and process A receiving this response. So that's a round trip. That's not just end to end. and that's just in 4 microseconds. I think that's pretty good, pretty impressive. Now, when we're talking about APC, one thing that we need to touch is marshalling and unmarshalling. It kind of both related to IPC and your code. So when you choose what tools to use for marshalling, you need to think, you need to test, and you need to be careful, because those can be the biggest contributors to your latency. So you need to probably choose the tools that are specifically developed for low latency. All right. Now, we'll briefly touch the hardware and operating system subject. So I will be really quick there, because for all this stuff, you can find more details on the internet. So do your homework. I'll just basically point out the subjects that you might want to investigate about. So basically this part is about how to make your code run faster without touching the code, by just tuning the operating system and tuning your hardware. And we start with CPU, which is like obviously the main contributor. In Intel CPUs, you have the concept of C states, and they kill the latency. They are really slow if you use them, so we just suggest to turn them off. Here is how you can turn them off. Basically, by using these parameters, you tell your processor, please don't be environmentally friendly, don't be energy efficient, just run at full speed always, and just run at the highest possible frequency. Now, turbo boost is another bit contributing to the CPU frequency. It's usually enabled, but sometimes in BIOS they disable it, so please check your BIOS, make sure that it is enabled. It is a really good thing. Although keep in mind that it depends on the thermal envelope of the processor, and be aware of the AVX throttling. If you use the AVX instructions, the turbo boost limits itself. Turbo boost frequencies are limited by the processor. So do your homework and Google about it more. CPU caches, just keep them in mind. Try to write code that is CPU cache friendly. That's what mechanical sympathy is about. And use the correct CPU governors if you use Linux, and I assume you use Linux if you're writing ultra-low-latency. If you're using Windows for ultra-low-latency code, good luck with that. You're probably doomed. To use the performance CPU governor, there is a command there that you can use. Performance CPU governor basically says, CPU, please do run at full speed all the time. Don't ever clock down. Now, very important point is CPU pinning. You do want to isolate the operating system threads from your application threads. So you want the operating system to use some processors and your own microservices to use some other processors. For this, you use the isol CPUs command in the kernel line. Then you want to isolate IRQs, probably, for the same reason, so that you are able to pin your application threads to the CPUs which are not used by anyone else, not by operating system, not by other threads. And this way you will achieve the best performance from the single thread. And basically you can run a set of microservices on the one machine. So say you have 32 core machine, you give 4 cores out to the operating system, you've got 28 left, and those 28 cores can be used for say 20 processes, each single threaded, pinned each other to its own CPU, and running without any issues between each other, without any context switching, without any of this stuff. They will be running really fast. Now, memory. You don't want to use swap. Everyone knows that's how you can disable swap. I don't want to go into too much details here. That's basics. Next thing is NUMA. If your CPU is using NUMA architecture, and probably you are using NUMA architecture if you have more than one physical processor, then you need to be aware how it works. Basically, it works like it's pictured here. You have the processor, but basically each of the process sockets is attached to particular memory controller, and for the processor in the NUMA node 0 in this particular example, to access the memory in the NUMA node 1, it takes much more time than the local access to the memory local to this NUMA node. So you want to avoid it at all costs. So ideally you would want to reserve the CPUs for the operating system on one NUMA node and reserve processors for your own application on the other NUMA node. You would be using NUMA-CTL, playing with it, and you would disable the node interleaving. So basically the operating system will not try to use memory from the foreign NUMA node, let's call it. Next is transparent huge pages. While transparent huge pages are very important addition, were a very important addition to the Linux kernel, for our use case, for microservices, for ultra-low latency, they're really, really bad. You can read more details on this link. I don't want to go into too much details here, but they are bad. Disable them, and that's how you can disable them. Disk. You obviously want to use SSDs, everyone knows that, not too much to say there, and you want to disable the I/O scheduler if you're using SSD, because SSDs usually have their own scheduler, so you don't want your kernel to do the job of the disk controller, because this controller will do it anyway. So that's how you disable the scheduler. Next, file system matters. You do want to use ext4. We had a bunch of testing performed together with Lenovo. We tested XFS, we tested ext4. ext4 is much faster with these particular parameters. So obviously these parameters disable some safety features. So use them at your own risk. Your mileage may vary. Do your own tests and think before you do. Kernel operations are expensive. We all know that. So we do want to use kernel bypass, for example. Solarflare network cards are not using kernel operation, they use user space operation, so they are much faster. Memory mapped files, memory mapped writes are user space writes. Operating system flushes the data to disk asynchronously from the operating system threads. It doesn't affect your application threads. So that is another reason why memory mapped files are good for performance and for ultra-low latency. Now let's wrap up a little bit. I covered topics of what is latency. We covered an example, and we covered various points, not necessarily connected between each other, of what we use to make microservices fast. So I think by now I proved to you that microservices ain't necessarily that slow thing somewhere in the cloud that most people associate the word microservices with. Microservices can be really, really fast, and we did this, we implemented this, and so we proved that they can be really fast. We have a fully operating system deployed at one of our clients, full order management system, which basically works in under 19 microseconds end to end, wire to wire, from the point the system receives a message from the client, from the remote client, to the point we send the response to this client with like multiple hops inside. So that's really fast. Another takeaway I want you to remember is the JLBH. JLBH is really good, so we do encourage everyone to use it, to give it a try, and probably you will get addicted to it, and you will get addicted to benchmarking, so beware. And finally, we covered the topic of environment, and do remember that your environment can be your friend or it can be your enemy. The choice is yours. do your homework, do your tests, learn more about what hardware you're using, how to better utilize it, and so on. And we'll see you next time. Thank you again for your attention. There is a bit of advertising here. There is a LinkedIn group for Chronicle Performance Engineers. Please join. There is Peter Lorry's blog. There is my blog, where there is only one article. And there is Chronicle Software website and our GitHub. Please visit. Please subscribe.
They're going to be extremely useful, not just for those who are interested in low latency, but in generally in much better performance, especially when it comes to concurrency, garbage collection, which is a pretty common problem for all managed languages, as well as kernel tuning, which is actually something that, like at least some of the techniques are totally useful for containerized environments or even mobile development setups, since background noise during performance measurements is a common issue. Also, well, let's switch to the questions now. So looks like we don't actually have a whole lot, but we do have a question from Arun. And the question is, what are the typical use cases where you've used these techniques for ultra-low latency? Can you share some details to understand how these changes really helped in a business context?
Well, funnily enough, I already answered this question at the end of the talk. So the question came just somewhere just past the middle of it. But the example I gave, well, first of all, the main clients of ours are big companies, big financial institutions like banks and big hedge funds and so on and so forth. And majority of applications we help them with are big trading apps. And for those trading apps, we can achieve microseconds end-to-end latencies for in particular pricing and trading. So one of the examples we had is the application we developed in one of the banks with 19 microseconds end-to-end latency for the trade. So from the price coming in, from the request coming in to all the processing, credit checking and whatnot, and up to the sending the response back. So that's basically the major use case at the moment.
Awesome. Jay is asking, is it really possible not to have any GC at all, as you mentioned?
Yep.
Yeah, actually, yeah, sorry,
well,
go ahead.
To clarify, right, you probably will have some GC at the very start. So when you just create stuff, when you wire up stuff, you just pre-create everything. You pre-allocate memory, pre-allocate all your arrays if you need some, and so on, and then you are done, pretty much. From that point onwards, you don't need to deallocate objects. From that point onwards, there is no job for GC to do. Are we not losing benefit of having heap memory? No, we're not. But also, we are actually extensively using off-heap, as I mentioned in the talk. So we do use manual memory management quite often, and that's one of the trade-offs you have when you're developing, when you are trying to do something ultra low latency in Java. There are things in managed environments, and Java is one of the managed environments, which you cannot control unless you kind of do some tweaks. And one of the tweaks is just avoid garbage. This way, the managed environment will not try to interfere with you.
So I think Jay is continuing asking questions. So are we not losing the benefit of having heap memory, particularly where we deal with large reports and complex computations with so much data?
There is no problem with the amount of data when you use it off heap. So you put all your data off heap and you just access it. You know where it is. And there is no problem with complex computations.
Yeah, in fact, a lot of interesting serialization or encoding techniques, like, for example, simple binary encoding, they frequently use a flyweight pattern where you just essentially do, it's kind of similar to the cast in C world, where you just cast your bytes from mmapped file into a in-memory like structure, and you get all the benefits from type safety, but at the same time you also don't need to serialize anything, and so you don't lose anything, you just gain fast performance. And so Jay is still asking, would you really like to try these options to check how it helps in my area of projects? Possible to share the presentation pack?
Well, that's a question for you, I guess.
No, it's probably for you, but you can probably sync with Jay offline. I think it's probably, he's probably curious about using some of the techniques that you've mentioned. Anyways, we can probably discuss.
Yeah, I do encourage you, Jay, I do encourage you to visit the OpenHFT GitHub page. We have quite a lot of documentation, especially around the queue, around the bytes and wire projects, and those are the main that I used. So Chronicle Bytes is the underlying, the low-level library for accessing memory mapped files, and well, for accessing memory in general, and for writing low-level data. The Chronicle Wire built on top of it and is used for marshalling and unmarshalling stuff into bytes, and then Q is the full-fledged transport that you can use. So have a look at documentation, and always feel free to ask anything on Stack Overflow. We are pretty active on Stack Overflow, and of course LinkedIn.
Oh, that's really good stuff. We're actually a little bit over time, but I just had the last question, I guess. I was just curious. So, like, many of these advices, especially around data structures, are extremely applicable for mobile world as well, because the GC is actually usually even much worse on platforms like Android, and it's much more expensive. And so basically using better data structures, not default ones, is very common for Android. But the issue is that it's oftentimes hard to find the optimal one. And also, even if you do happen to find the optimal data structure for a specific use case, as time goes on, it may happen that like your use case basically changes, or maybe in production you have different modes of operation where you have, let's say, one of the users who has, let's say, I don't know, tons of tweets, right? And so one data structure may be more applicable for one use case, and then for a different user you can have a much smaller collection where a different data structure would be useful, which means that there is basically no best data structure that you can just know in advance. So do you have any advice on how to find the best data structure, and then also make sure that as your use cases evolve, your data structures evolve with the changes in use cases?
Well, I would say, again, I touched it slightly. So there is Coloba Collections library by Roman Leventov. He used to work for Chronicle, by the way. So he's a smart guy, that's by definition. This...
Yep, sorry for interrupting. It's just, I get it. Like, there are data structures that are like really good, but they don't work well for everything. Like, you need to know your use case. Like, you need to specialize for use case, but your use cases change all the time. So ideally, you'd want to have data structures that adapt automatically, not something that you statically choose at compile time or when you build the application, but something that can basically be kind of like JITted, but on a macro level, where imagine that during your execution of the application, we detect that the size of your data, for example, works better with, let's say, linked list implementation. I mean, linked list is probably not a great data structure, but anyways, like I mean, this tuning can be dependent on the use cases, not static. So it's good to have the selection of these data structures, but I'm just not. I was just wondering if you know if you use any techniques to do this data structure selection dynamically or based on use cases automatically.
No, we don't use any dynamic restructuring of the data structures. That's one thing, but I would really argue that I can't really imagine the use case to change like online all of a sudden during the runtime. I would probably guess that the use case might change when you change the way your application works, and that means that you would be probably recompiling, redeploying it. And at that time, you can always adjust the data structure. I haven't seen the use case yet. Maybe I'm yet to see it, but so far I haven't seen the use case for dynamic adjusting of what you use underneath. But,
yeah, we often
again, I'm not a mobile developer at all. So I haven't got any experience with that. So maybe there is some there.
Well, for backends, we also have this. It's a very common issue because different users, let's imagine that, for example, you're building something like Twitter, and some users have a lot of followers, some users have very few followers. And if you, for example, if you want to use a set data structure for just one follower, you can actually have a very efficient implementation that just uses like a single element. Like, so there is no, hash table or anything like that. You just store an element directly inside of your instance, and then your checks are constant, your memory usage is constant. It's really good. But then for other users that have a ton of followers, for example, you may use a different data structure. But that's actually, I guess, an intro for one of the talks that we're going to have next about dynamic optimizations and stuff. So yeah, thank you so much again, Dmitry, for your talk. We're going to have a very short break just because, unfortunately, we are out of time again. And then we are going to pick up with the optimizing computer systems in complex and dynamic parameter space by Eiko, which is actually somewhat related to the topic that we've just discussed. So yeah, see you in a minute. Thank you so much.